Hi everybody, welcome back to another video. I wanted to create one more video about using an example over all the stuff we've talked about in the last few videos, about how f prime and f double prime relate to the graph of f of x. It says find all intervals of increasing or decreasing, find all local maximums and minimums, find all intervals of concavity, so where's your graph of f concave up, where's it concave down, and find the inflection points. Let's just go ahead and jump right in. And so since we're finding intervals of increasing or decreasing, local max and mins, and intervals of concavity, it seems natural that we should probably want to find f prime and f double prime. And so I wanted to have one example where we kind of put together the whole entire structure that we saw in both of the last two videos. So I hope that you have an idea of what to do with this before we even jump in. What I want to do is set up a kind of a table or a number line like this and look at specific values of x and then kind of test intervals on either sides of those important points for us in both f prime and f double prime and see what does that tell us about f of x. So let's just kind of copy and paste here for a second. F of x was x to the fourth minus 2x squared plus 3. Okay, so you should want to find f prime of x. And f double prime of x. All right, and then I hope you have an idea of what to do with these now that we've found them. If this was not a polynomial, if this was a function that was a little more complicated, that where the domain wasn't all real numbers, we would have to look for where does our function not exist as well. Remember, part of critical points was where is f prime undefined. So since the domain of all of these functions is all real numbers, all we have to do is set them equal to 0 and solve to find critical points and then also to find our inflection points. So in the first one up here, you can factor out a 4x. If you factor out a 4x, you get something like x squared minus 1. And so that should give you values like x equals 0, x equals positive 1, and x equals negative 1. And let's see, in the second one, we can take this one, set this equal to 0. You could actually factor out a 4 and divide everything by 4. And that would give you something like 3x squared minus 1 equals 0. And if you add 1, divide by 3, that means x squared equals 1/3. Square root both sides, x equals plus or minus a square root of 1/3. Or if you want to reduce that, or rationalize that, I should say, you can write it as square root of 3 over 3. I don't really care that much, so I'm going to just leave it as 1 over the square root of 3 like that for now, if that's okay. So look at all the different points that we have that are important points for us that we're going to put on our number line. We're going to put 0, 1, and negative 1, and we're going to put plus or minus 1 over the square root of 3, or square root of 3 over 3, there, if you're rationalizing. So I almost don't even have enough room to put this on a number line because we have 5 different points to worry about. That's kind of a lot. So let me go ahead and put them over here, and then we're going to kind of build up from here. To the furthest to the left is negative 1. And then somewhere in the middle is 0, and over here to the far right is 1. And then I think you have, let's see, 1 over square root of 3 and negative 1 over the square root of 3 should be somewhere in between here. I didn't figure out what those are as a decimal, but there you go. If those are in the wrong spot, I need to be a little bit further over to make my scaling appropriate. I'm sorry about that. But either way, they're between 0 and 1. Okay, so what we want to know about here is what happens with f prime, what happens with f double prime, and what does that tell us about f of x. Here's what I like to do as far as my structure. I'm going to put my test values on the top, just so that I don't confuse those with these boundary points on the bottom. And so I don't even want to write test values. I'm just going to write test. And then I want to know what happens with f prime and f double prime, and those are going to tell us what happens with f. So this thing's going to get pretty big. It's going to take up a whole entire page for me. And so remember that some of these values on the bottom came from places where f prime was equal to 0, and some of those values came from where f double prime was equal to 0. So we know what some of these values look like, but not the whole table for sure. So 0, 1, and negative 1, those came from setting f prime equal to 0. So if you look at -1, 0, and 1 for f prime, you're going to get 0 for those values. But you're not necessarily going to get 0 for f double prime. In fact, you're for sure not going to, because otherwise we would have solved in the other place. Now, where the 1 over square root of 3 and the -1 over square root of 3 came from was setting f double prime equal to 0. So you might ask a question like, well, what happens when you plug in 1 over the square root of 3 into f prime? Like, what should go right there? And then what happens if you plug in -1 over the square root of 3 into f prime? What should go right there? Okay, and so we can look at those and let's see what we should get. And when I did this and plugged in 1 over the square root of 3 into f prime, I got something that was negative. It ended up being something like negative 1.5396 or something like that. When you plug in negative 1 over square root of 3, I basically got the positive version of that decimal. So right here, you should get something positive. All right, so I don't need boxes around stuff to make this structure more complicated. It's already pretty complicated as it is. So I'm going to try to just leave it so that we have kind of bare bones here at this point. But let's think about this. So if f prime is positive at -1 over the square root of 3, what does that mean about f? So think about what it means if f prime is positive. That means f should be increasing. And again, kind of like what I did in the last video, I'm going to go ahead and I got to draw it pretty small here, but I'm going to put a little increasing going up to the right like that. And then when f prime is negative at 1 over the square root of 3, that means that f is decreasing. And I'll go ahead and put a little thing right there. Okay, so at x equals 0, right here in between, f goes from being increasing to being decreasing. We should get a local max there at x equals 0. Okay. So just good to keep track of, because again, we're not just trying to find intervals of increasing and decreasing, we're trying to find maximums and minimums as well. Now we haven't kind of checked over here on the right side and on the far left, so let's go ahead and put -2 over here to the left and 2 over here to the right. Now you might say, well, wait a second, we used 1 over root 3 and -1 over root 3 as a test value. We did. In fact, I could kind of put them up here as test values, but we also use those values because we know how f double prime behaves for those. So they're not unspecial, basically. They're still really special points for us. They just have more to do with f double prime than f prime. But since they were already there on our number line, we may as well use what we already have. Okay. So what happens when you plug in 2 and -2 into f prime? And I think you should get that when you plug in 2, you get a positive, and when you plug in -2, you get a negative. Okay. And so again, what does that mean about f? Well, that means f is increasing on the interval from 1 on, and f is decreasing on the interval from -infinity to -1, because that's where f prime is negative. Okay, so again, I'm going to go ahead and put my little visual aid here. And notice we've done a lot with f prime so far. We haven't done a lot with f double prime yet. Okay, so we do know where f double prime is equal to 0. It's equal to 0 at those 2 inflection points that we found, which was plus or minus 1 over the square root of 3. We still have to test some other values, though. I would say let's test everything else that we haven't used for f double prime. So let's test 0 and see what happens when we plug in 0. But this time we're not plugging in into f prime, we're plugging in into f double prime to find out what do we get right here. Okay. By the way, the fact that that's a local maximum, I think we probably should have an idea of what's going to happen. We should just verify that. If that is a local maximum right here, that means the graph's going to do one of these. You should expect that it's probably going to be concave down between those values. So just a good thought, but let's just double check that a second. So what happens when you take f double prime of 0? I got a value like -4. Again, we don't really care that it's -4. I really just care that it's a negative. So it's a negative as we thought. That means it's going to be concave down. Go ahead and take a second and plug in 1 and -1 into f double prime and figure out what's going to be happening with f there. This is actually a fairly symmetric graph. When you plug in 1 and -1, I think you should get, I think it's 8 for both, but really all we care about is that it's a positive there, and you get a positive there. Now you might be asking yourself, what do I need to test 2 and -2 in f double prime? And you actually don't. The reason you don't need to test 2 and -2 in f double prime is because those are kind of on the same interval as 1 and -1 were. There's no inflection points in between 1 and 2. And so you don't need to kind of test 2 different points on the same interval. You just need to test 1. So the fact that we have f double prime being positive at x equals 1 means f is concave up. We already said that where f has a local maximum, f is concave down in the middle. And then on the leftmost interval where you plugged in -1 into f double prime, f is concave up there as well. This is a ton of information in a table like this. Let's see if we can summarize some of the things that we think we found. Remember, we're trying to find where f is increasing, where f is decreasing, where f is concave up, where f is concave down, and along with those were critical points and inflection points. Let's see, was there anything else we were trying to find? Let me go back to my directions. Intervals of increasing, decreasing, local max and mins, concavity, and inflection points. So local max and mins, I would say that kind of falls under critical points, but we got to characterize them as being max or mins. So let's go ahead and see if we can kind of put all this together. What does this tell us? Where is f increasing? Really what we're looking for is the stuff at the very top. But there's so much information up there that comes from the information down lower in the table. Okay, f is increasing here. Where is that? Well, that happens between critical points. That was actually between -1 and 0. We tested the value of -1 over root 3, but that was because it was a value between 0 and -1. So f is increasing on -1 up to 0. And if we go back, f is also increasing at the very end after x equals 1. And remember, x equals 1 was one of those critical points. So it's also increasing on 1 up to infinity. Okay, let's see, where is f decreasing? Kind of the same idea. It's decreasing at the beginning and then on that third interval between 0 and 1. So f is decreasing on -infinity up to -1. And it's also decreasing on the interval from 0 to 1. And really, it should be decreasing basically on every interval where it's not increasing. So if you know where it's increasing, you can just kind of use the other intervals for one like this. Okay, concave up and concave down. There were 2 inflection points on the bottom. So there should be 3 intervals where we have concave up or concave down. And so this is concave up on the interval from let's see, from -infinity all the way up to our first inflection point. So 0 up to -1 over square root of 3. And then it also looked like concave up after this, on the last interval there, from 1 over the square root of 3 up to infinity. And then this is concave down in between there from -1 over the square root of 3 up to 1 over the square root of 3. And then we kind of already talked about these max and mins. The inflection points we already know we're at plus or minus 1 over the square root of 3. And then there is a max, a local max, and local mins. Let's see, we know there's a local max at 0 in the middle. And then if we look at the other intervals, we go from decreasing to increasing, and then decreasing to increasing. We should have local minimums at -1 and 1. This is a lot of information for us to find, but it comes from the structure and finding what's f prime and f double prime look like. All right, hope you've enjoyed the example.